Calista from University of Alberta, the CCWJ, and he's going to be doing a presentation on the modeling of electric resistance welding and heat input.
Thank you. Hello everyone, my name is Daniel and I'm very excited to talk to you today about some of my recent updates in my thesis work on electric resistance welding. So my thesis is studying a certain defect in electric resistance welding. They're called penetrators. I'm going to give an overview of that in the presentation, but the presentation is going to segue from an overview of the process to heat input in the process to the defects, and then I'm going to conclude with some updates about modeling the process and the heat distribution of the process at the end of the presentation. So what are we going to cover today? We're going to peek into the ERW process using a regime perspective. Why do we want to do this? We want to understand certain process conditions and how they relate to generating defects in the process. Why do we want to do this? Understanding process behavior is crucial to improving productivity and reducing costs, which at the end of the day is what we're all here to do. So I'm going to set some context and introduce you to the process for those who aren't familiar with it. Electric resistance welding is used for seams tubular goods most commonly, so such as oil country tubular goods like line pipe, heat exchanger tubes, mechanical tubing, electrical conduit as well. Key sectors include the oil and gas industry, the automotive, the structural and the chemical sectors as well. The process is uniquely, extensively multi-physical and coupled. What I mean by that is if you look at this figure here from Egger et al., they conducted some simulations here. The major thing with this process is that we're regarding the interactions between temperature fields, phase transformations, mechanical deformation, and in the electromagnetic interactions as well. So there's a lot going on in the process, there's a lot to understand, and there's a lot to sort of select out when you're modeling. There's a lot to say, okay, I'm going to regard this stuff and I'm not going to regard these, just to simplify the problem to model it in an adequate manner. And because of this coupled nature, it's very difficult to reproduce in a lab setting. These plants are 500 feet in excess, longer than that, and just to make an ERW weld product. So you can do small scale Gleeble testing, but the miniaturizing the process doesn't retain all of its characteristics on the full scale. So full scale testing is generally the only way to get a representative demonstration of the process. So a quick video, you take an inlet scalp of sheet material from a rolling mill and you feed it through some rollers. There's successive deformation to the point where you get a circular product, and then after the successive deformation, there's usually two types of ERW that you can have, either a sliding contact type or an induction coil type. Both of them, for all intents and purposes in this presentation, are going to do the same thing where they are inducing current in a weld V, whereas you merge the two interfaces. Those interfaces heat up, there's sometimes a liquid film, and then there's physical upsetting between the two, and then you get a metallurgical bond. Yeah, they're pretty simple. So the general problem in my work, ERW, or high frequency welding, is another name that's known by, they play an integral part in society's infrastructure expansion and development. Line pipe is very crucial. The continuous ERW process boasts, compared to other alternatives, autogenous joining, so no additional filler metal, high productivity rates, and low operational costs. When we compare this process to, say, direct submerged arc welding or seamless tube milling, it's a lot more efficient. We can run at a lot higher speeds, but the drawback: continuous seamed products from ERW can exhibit comparatively low toughness when compared to like seamless and direct submerged arc welding products. And why do we care about toughness? Well, toughness fundamentally represents a material's resistance to failure. And this resistance to failure is very crucial in emerging energy sectors such as low temperature service and hydrogen service, both of which require tougher components to withstand these load conditions. So the actual scientific problem in my thesis, the penetrators themselves. Toughness in ERW components has been known for 40 years to be directly related to penetrators. What are penetrators? They're elongated microscopic and trapped oxides, usually the manganese silicon variant. And the key thing about them is that they are evenly distributed along the bond plane of an ERW weld. So this is a cross section of an ERW weld. The pipe is running in and out of the page. And because they're a manganese silicon variant, they actually solidify after the surrounding metal. So after the steel's been joined, the metallurgical bond's been made, they're still liquid. And there's evidence of this just by these micrographs here. Because they have a pervasive and distributed nature along the bond plane, Like I mentioned here, they can facilitate fracture very easily because we have them all in one plane. Cracks can go through like nothing. And there's an example of a ductile Sharpie test. And you can see a bunch of penetrators, or a grouping of penetrators here that have a local cleavage plane here. Penetrator composition has also been linked to size. So there's been some studies in the mid-2010s to 2020s that have observed this. So there's some evidence that they have this thermodynamic growth and kinetic growth aspect to them. That's not going to be explored in this presentation, but I can touch on it if you like. So addressing penetrators themselves. How has industry tried to tackle this problem? Because the industry's been seeing them since the 1980s. One method by JFE Steel in Japan is to do closed loop control by in situ phased array ultrasonic inspection. So this is downstream of the weld zone. After welding, they have essentially correlated an impact energy from Sharpie impact testing to an acceptable level. And since impact testing is related to penetrators, they're saying, okay, at this impact energy, we're okay with the weld seam condition. And they've correlated that impact energy with a UT signal, specific echo level percentage in their machines. And so they're saying, okay, in this process, downstream, we're observing this echo level. How are we going to tweak now input to ensure that we're not making penetrators? They developed a system for this. Another one is closed loop control at Nippon Steel that was joint with POSCO Steel in Korea. They couple optical monitoring of the weld zone. So this is a top-down view of the weld zone with electrical data acquisition, which is frequency and voltage monitoring. You can see there's specific voltage waveforms that correlate to certain weld zone conditions. And so they have a system that's tweaking heat input based on these conditions. However, both of them lack a physical understanding of why penetrators occur at certain welding conditions. These are band-aid solutions. Industry's just trying to optimize the process based on what they think works. They're not understanding what ERW conditions are leading to penetrators. And that's where my project is positioned. So before we move forward, we're gonna understand the ERW process and its key sub-mechanisms. One is the current distribution. I'm gonna demonstrate the induction coil setup here. So for all intents and purposes, downstream of the V, the current between the contact slider setup and the induction setup are pretty much the same. AC frequency we're using in ERW, so direction is, it flips back and forth. But say we're going this way, we have current that goes down the V at the V point here, switches back, and it couples itself. So essentially the weld interfaces here are two almost independent conductors in space. And I'm going to touch on that. Why? Because there's two electromagnetic effects that are prominent in ERW, and that's the skin effect and the proximity effect. Why do we care about them? They naturally help localize current, and they increase heating and melting efficiency. So what is the skin effect? Say we have a low frequency AC conductor, so a coil that's running, or a wire that's running out of the page here. This is what the current distribution is mostly going to be. Most of the current's going to be distributed across the section with very little in the center. As we increase frequency, your current is going to focus more to the outer edge of the conductor, and the effective depth that represents where most of the current is localized is called the skin depth. It's represented by this relation. The analogy for this is why large-scale transmission lines, if you cut them, they're made up of smaller copper cabling, and that's because of the skin effect. The other effect that we're going to talk about is the proximity effect. I mentioned that if you have the two interfaces, the current's going one way in one interface and is going the opposite in the other. So there's some degree of inductive coupling between the two, which also concentrates current on the weld interfaces. So bottom line, these effects help concentrate current and heating to the weld interface to do minimal heating, have a minimal heat affected zone. And then there's also another concept called electromagnetic pressure in the system. So electromagnetic pressure is a result of the Lorentz forces generated in the V. So here's a top-down view of an ERW weld where we have the geometrical apex convergence point where the two interfaces want to meet, and then the weld point's actually shifted downstream. I'm going to touch on this in a few slides here. But you can see that these points aren't shared. They're not the same space. And the reason why is because of these forces. So as you go towards the weld point, and the current would follow this path here, your current density is going to increase. And current density is directly indicative of these Lorentz forces, which act actually normal to these weld interfaces. And so they actually cause the expulsion or the opening of the V. So that's a key aspect here. So now we're going to look at how those effects link to the heating in the process and then how that links to penetrators. So the process problem. ERW is highly dynamic and there's complex phenomena that are occurring. Industry commonly uses 3 classifications to sort of say, okay, we're in a low heat input range, we're in an optimal heat input range, and we're in a high heat input range. So there's 4 general phenomena that have been loosely linked to penetrators. The first is a narrow gap effect. I just briefly touched on this in the pressure slide, but you can notice as your heat input or power to the V is increasing, a narrow slit starts to evolve downstream of that apex point, and your weld point starts to shift down. So that's a narrow gap effect that's related to the electromagnetic pressure in the process. There's also been observed arc flashing periodically at a fixed point in the process. And there's also, this flashing leads to a molten metal bridge that connects the 2 interfaces, and that the movement of that bridge downstream and upstream in the V is thought to be indicative of penetrators. And these 3 effects can lead to molten metal refilling. So this is a top-down schematic of the V, and this red metal here is metal that has been expulsed out of the V. So it's out of the V, and when we have hot metal that's molten outside of the closed interface in an oxygen system, you can get oxides. So when this metal is thought to re-enter the V, that's when we get oxides in the weld zone, and those are the penetrators that we're talking about. So about those heat input classifications, industry uses arbitrary designations to date to try to understand the process or represent the process. There's 3 key points that have been presented by Nippon Steel. One is the geometrical apex point that I talked about, where it's the actual point where the 2 weld interfaces want to meet based on just a linear extrapolation. The second point is the point of first contact, where the 2 weld interfaces are actually first touching each other. The third point is the actual point of welding, where there's a metallurgical bond formed. These 3 points necessarily don't have to share the same point in space. When you're in the low heat input condition, they do share the same point in space. As you increase power to the V, your weld point starts to shift downstream. And then as you increase heat input further, your geometrical apex point, your point of first contact, which would be that arcing point that I mentioned earlier, and your weld point, they all are separate at excessively high heat inputs. This concept has been presented as an attempt to objectively classify the process, but it's yet to be rigorously explored. So flashing and bridging events. So periodic flashing occurs at a specific point, let's say here, and we're going to mark it by this line here, and the weld point in this process is marked here. Okay. Immediately after an arc flash event occurs, you get a molten metal bridge that forms, and that bridge starts to move downstream the weld, downstream. And the weld point starts to shift upstream the weld. After that, eventually the molten metal bridge is moving downstream, hits that weld metal that has been moved up, and now both of them start to move back downstream in unison, eventually until the original conditions of the process was achieved. This is the periodic nature of the process at high heat inputs. How does this relate to penetrators? Well, the effects of this bridge movement have been thought to link to penetrators by a specific sort of arbitrary diagram in 2009 by some Korean researchers, and it's an untested theory of the coupled effect of flash frequency and bridge speed. What is this theory? So, the first stage, we have your current path, say it's going this way, around the V. We have electromagnetic pressure generated inside the V, okay? When an arc flash event occurs, you get a molten metal bridge that occurs, and then now you have an electrical short circuiting through here. So now, after the short circuit, you still have your electromagnetic pressure behind the V, but you have nothing downstream. And because this is a narrow slit, 2 things can happen. 1, you have pressure behind the bridge, so the bridge is going to move forward. And 2, capillary forces can allow this weld metal or this weld point to shift back up. Eventually, your bridge, which is the main point of your circuit contact here, it meets the weld point. And this is the theory, is that if you have another flash event that occurs before that bridge completes its full sweep of the V, then now you have another short circuit here, and this bridge is retained. And this bridge essentially sucked back oxidized molten metal, which is what the penetrators are essentially. So those are the thoughts about how an unstable weld zone can lead to penetrators. Those have been presented, in that last concept was presented in 2009. Nobody has studied it since then. I'm going to try to link a heat model, an analytical heat model, to process stability, which is indicative, we see is indicative of penetrators. So let's look at a diagram of ERW for our model. We have the V length here by L, the plate thickness by D, and our V angle here. For all intents and purposes in the rest of the presentation, we're only going to be looking at temperatures at this weld point, okay? The model that I have can account for the transient heating effects over the V, both before and after, but we're only going to be looking at this point in the rest of the presentation. So some key concepts before I present the model for the results. Dimensionless groups. I'm not going to give a rigorous definition, but I'm just going to say how we can use them. So say you have two process parameters, A and B, and you want to know how they affect the process. You're going to say, okay, if you divide A and B, the division of those two, when that division gets super large, A is going to dominate B. And when the division of those two is super small, B is going to dominate A. And your process is going to be a function of those two. So that's how we're going to sort of view the process. We're going to divide certain parameters to get their dimensionless counterparts that are going to be unitless. And then we'll be able to say, okay, as this number gets big, the process is dominated by X. So we mentioned the skin depth earlier. I'm going to introduce a new concept here, thermal depth. Well, it's not new. Our lab has been studying it for a while. And this essentially represents the heat penetration into your substrate. So, for example, in MIG welding, your travel speed, which is just represented by U here, if you move really fast, you're not allowing time for heat to penetrate into your substrate, so your thermal depth is going to be very shallow, and that's represented by this relation here. So, in ERW, if we take the division of these two as delta star, our dimensionless group, because this is meters over meters, we can essentially use this to predict temperature behavior or process stability in ERW at the weld point. And so, based on this dimensionless group, we have two potential modes that we could be operating in, two regimes. One is the electric mode, and that's when you have the amount of volume of material that is conducting current is larger than the amount of material that is actually being heated. You're in an electric mode. And when the amount of material that is being heated is larger than the amount of material that is carrying currents, which is the yellow region here, you're in a thermal mode. That's the idea here. So as your skin depth gets really small, you essentially get a surface heat source, like laser heat treatment. So again, we're only looking at the weld point. If we plot dimensionless temperature at the weld point, again, along process conditions, which is this ratio here, and this ratio is representative of your V length, your travel speed, and your operating frequency, we get this curve. Now, in terms of for an operator, this curve means nothing. Numbers mean nothing. What it means for the engineer is the shape of the curve is important. If you zoom in and you look at the curves really closely, you'll see that it behaves in two asymptotic ways. One is, as you go this way, as your delta star, your thermal depth gets really large, the curve behaves asymptotically linear. And as you go really small, the curve is more curved, and it's asymptotic as your delta E gets really large, as this ratio gets small. This leads to the thought of a transition point and the two different regimes in the process based on this dimensionless group. And this transition point can be explored further. So this is a process stability curve. What does this represent? Again, these numbers are meaningless, but it's the shape of the curve, or the relative magnitude of the numbers are meaningful in this case. So if we look at this, when we're in the electric regime, our delta star, our thermal depth over electric depth, is going to be small, because we're dividing thermal over electric. We're in the thermal regime, electric regime, and because it's really small, our process stability is very low. Or instability is very high. What does this mean? In the ERW process, the V length, the frequency, and the mill speed change sometimes. The mill speed and the V length are usually fixed constant for large scale analysis, but the frequency bumps a lot. We saw those waveforms a lot earlier in the presentation, with the frequencies going up and down by about 3 kilohertz to 5 kilohertz. Those bumps can lead to a change in V temperature and V stability. So when we're in the electric regime, we have more of our weld metal that's being dominated by current. So a bump in frequency is going to affect more of the material. So here we're less stable, here we're more stable. This is the thermal mode over here. What do we know about this? These dimensionless groups, or this ratio, tells us that as we increase V length or we increase frequency, we're going to be in the thermal mode, which is what the operator wants to be in. If we increase mill speed, we're going to be in the electric regime, which is what the operator doesn't want. That's what this is saying. So some noteworthy items to do this testing. You need a full-scale ERW mill. You also need high-speed thermal imaging to actually validate the temperatures that we can measure, predict with the heat model. Also, frequency and current monitoring would be beneficial because we want to link unstable process predictions by temperature with the unstable process conditions by frequency monitoring. Large-scale ultrasonic testing and/or destructive testing is necessary because we are predicting penetrator formation by process instability. And so we'll say, okay, at this point, this process was unstable. We think there's a penetrator there. How do we tell? We have to crack it open. So that's why we need the destructive testing. Some notable difficulties with this project is quantitative temperature measurement. In ERW, you have multiple materials in the weld zone. You have your liquid film and then you have your solid gradient. And getting a temperature measurement of liquid steel is very difficult. On the ERW scale, robust and accurate data systems that sync with high-speed cameras are tough to come by unless you are the manufacturer yourself. And then ultrasonic testing is highly sensitive to other conditions such as your grain size, your temperature, and other conditions. So it can really only find large penetrators or large groupings of penetrators. So some final remarks. ERW process parameters can be evaluated by the ratio of theoretical reference depths. That's the thermal depth and the electric depth that I was talking about earlier. They behave asymptotically with respect to the skin depth and the thermal depth, which means that it has two different modes or two different potential regimes of operation. ERW temperature stability at the weld point will increase as your V length increases, increase as your frequency increases, or increase as your mill speed decreases. A noteworthy thing is that all three of these are not cost effective. Your V length is sort of fixed by your machine. Having a higher frequency in your system requires a more robust and expensive electrical system. And then running at a lower mill speed reduces production. So there's some sort of optimal point between productivity and a good weld. For future work, there's 2 points I want to touch. I want to assess the process stability criterion that I presented here against full-scale mill design of experiment results. And I want to finalize the analytical model of heat flow to produce a useful set of simple equations that industry can use. I don't want to present industry with a large equation. I want to present them with, like, here's this ratio, take it, and then you can do what you do with it. Some acknowledgements. I'd like to thank the CWB Welding Foundation for the scholarship that I received here yesterday, and Evraz North America for sponsoring my project, specifically Dr. Greg Lanhoff and Dr. Alejandro Hinchazaro. They've been really great mentors to me. So thank you.
Great. Thank you, Daniel. Are there any questions? We have a few minutes.
What about pre and post heat weld treatments of the steels? Do they affect the flash point and the throat of the gap?
So there's really no pre-weld heat treatment because the V, there's continuous heating along the V, so pre-weld treatment there's not really nothing done. Post-weld heat treatments, there's a set of stage of normalizations and annealing and quenching steps that the process is used. But the key thing to note is that these oxides, because they're retained in the weld zone, you can't get rid of them with heat treatment. So there's really nothing, once they're in there, there's really nothing you can do. So it's something that has to be addressed at the weld stage.
Maybe a really dumb question because I don't know anything about this process, but has they ever considered shielding gases to help reduce the oxide? Even on the top, at least you get 50% of them.
They have. Nippon has done plasma shielding, so they've actually shot a plasma jet into the V, and removing the oxygen environment successfully reduced penetrators significantly. Unfortunately, now you're running with a constant gas stream, so your cost of your process became astronomical.
You could use a cheap gas like nitrogen. You could heat it if it's taking heat away.
Industry wants to keep the process cheap and convenient, and the weld box is very. So for reference, their study only worked for 22-inch, 24-inch OD pipe, and the process is used all the way down to half an inch pipe.
I don't know, I guess if your process produces results that are not adequate for industry, you don't have a process, right? So you might have to, if you could develop a process that even increase the toughness by, I don't know, whatever, but just by directing some hot nitrogen or something at the surface, which is a cheap gas, you might have to preheat it, but then it would maybe get you over the hump on the impact.
So for reference, industry is kind of, they don't always get penetrators.
Yeah.
You can get large sections of pipe and product quality, high quality product pipe. They just don't, when they happen, industry just doesn't know why they're
So
happening.
they're trying to nail down
Why
why
they're
they have it sometimes and not others.
Exactly. So they don't want to have to run some like continuous jet stream when they don't really need it.
Yeah.
That's
makes
the main
sense.
issue.
Thanks.
One more, sorry, go ahead.
I just have a question. You touched on thickness of the pipe, or sorry, the OD of the pipe. Does that make a difference in thickness as well?
It can. The heat model does include that. The way I would think about it is if you have a larger surface area that's liquid, you have to do two things. One, your heating rate is going to be, your heat's actually going to be more distributed thinly on the interface. So you can still produce penetrators, but now you're going to have to squeeze harder in the process, because the squeeze process in ERW, its main purpose is to not just create a metallurgical bond, but also eject any oxide films. And that's why it's so difficult to understand how penetrators form, because industry says, okay, let's just keep squeezing until they push them out. But if you keep squeeze too much, now you don't have a circular pipe. So.
That's pretty fascinating. I've worked in some rolling mills and drawing mills, and to see it in real life and then to watch this is pretty fascinating. I really appreciate it. And actually, on behalf of the CWB Group, we'd like to thank you for your presentation.
Thank you.
And a big round of applause. The next presentation will be right away. Hopefully you've chosen where you want to go, because it's time now.
Good job, Daniel.
Thanks.
Thank you.
Thank you.
It